Assalamu alaikum, dear student. I hope you are fine and doing well. So today I come up with another one of my online session of cryptography. So, dear student, today the topic is one of the most important topic whenever you're taking a course of cryptography. Uh, right now, the standard which is utilized in all over the world is advanced encryption standard that you can see these kind of algorithm while you just setting your encryption while you using Wi-Fi security setting. In Wi-Fi security setting, you can see over there is a 2 to 3 types of encryption algorithm which are utilizing your Wi-Fi in order to secure your password and other digital information. Like it's a web AES, and these 1 to 3 encryption algorithm are inserted in Wi-Fi security. So today topic is AES Advanced Encryption Standard. It's pleasure to once again welcome you all. So dear student, advanced encryption algorithm is fundamentally the replacement of DES, data encryption algorithm. The advanced encryption standard is a symmetric block cipher chosen by US government to protect classified information, and it's implemented in software as well as hardware throughout the world to encrypt sensitive information. Dear student, the National Institute of Standard and Technology started development of AES in 1997 after some vulnerability in data encryption standard. When it is announced the need for successor algorithm for data encryption standard, which was starting to become vulnerable to brute force attack. Uh, Essential for computer security, cybersecurity, and electronic information protection, the advanced encryption algorithm would be unclassified and had to be capable of basically safeguard sensitive government information well into the next century, according to NIST announcement of the process for development of advanced encryption standard algorithm. It was actually basically intended to be easy to implement in hardware and software as well as is in restricted environment such as in smart card authentication and lightweight Android, and the offer the idea is that the if you have standardized some encryption algorithm, it must offer decent defenses against various attacks and other cryptographic attacks techniques. So, dear student, our idea today is to just look into advanced encryption standard. This advanced encryption standard is um, uh, one of the basic modern block cipher, which is secure against different type of cryptographic algorithms. So let us uh, um, define some objectives of our today class. First, we have to review a short history of AES to define some basic structure of AES. Then there will be some transformation used by AES, and then some key expansion and different and discuss some different implementation of different part of implementation of the different part of AES. So let us come up with some basic introduction. So these are some overview of our today class. Uh, Short history, how your encryption algorithm, basically advanced encryption and algorithm, who developed and what was the reason behind the development of AES, and what at that time how AES qualify among 15 different block ciphers. And initially 15 block ciphers was submitted to NIST, and then NIST uh, quantify five block cipher among 15 block ciphers, and then in these five block ciphers were tested with different programming languages, their speed, their analysis through NC, C, Java, and in order to authenticate their um, uh, validity against different cryptographic attacks. So, dear student, let us come up with some introduction, history of advanced encryption standard. The advanced encryption standard was published by National Institute of Standard and Technology in December 2001. The history, then we will in the in next slides we will discuss some history criteria, and then wrong data unit I mean to say what is actually the inside the what are the basic component of AES. It is substitution, permutation, shift row, mixed column, add wrong key, how the basic each and every component is actually working. Then we will discuss the structure of each round, how each round is working inside advanced encryption algorithm. So, dear student, the history, in February 2001, the NIST announced that a draft of Federal Information Processing Standard was available for public review and comment. Finally, AES was published in FIPS document in 197 in the register of Federal Register in December 2001. So these are all history, more or less some history about advanced encryption algorithm. The criteria defined by NIST for AES fall into three areas. The three areas, basically the selection process for new encryption, basically symmetric key algorithm was fully open to public scrutiny and comment. This ensure a thorough, transparent analysis of the design submitted algorithms. NIST specify the new advanced encryption algorithm must be block cipher capable of handling 128-bit block using key size 128, 192, and then 256-bit. Other criteria which in being chosen as a next advanced encryption standard must include some security, cost, and implementation. And when we are saying security, it means to say that competing algorithm were to be judged on their ability to resist different attack as compared to other submitted cipher through security strength, that is considered the most important factor in the competition. And then second was cost. Dear student, the cost intended to be released on a global non-exclusive and royalty-free basis. The candidate algorithm were to be evaluated on computational and memory efficiency. And then lastly, implementation, which is one of the important, how your algorithm, how easily your algorithm is can be implemented in hardware as well as on software level, or how it is algorithm is flexible, sustainable, according to hardware and software implementation, and overall the simplicity of standard algorithm. So dear student, there are AES is basically non-fiscal encryption algorithm, and basically AES encryption algorithm defines a number of transformation uh, that are to be performed on data stored in an array. The first step of the cipher is to put the digital information into array, after which the cipher in transformation are repeated over a number of encryption round. Whenever we say the round means in AES, there are basically three types of algorithm are quite famous with respect to round. That it uses basically 10 rounds, 12 rounds, and then 14 rounds according to key size. If you use 10 round, then it means your key size will be 128. Then if you use 12 round, then the key length will be 192, and then 256. For 256, you will have to apply 14 rounds. So it is quite noteworthy that AES defined three versions with 10, 12, and 14 rounds. Each version uses different cipher key, like we have discussed over here. So the first transformation that let me give the example in next slide. So the generally the here you can see over here in slide 6. Let me do it. So the general design of AES encryption cipher is of like this one. It has basically 10 rounds for 128 key size, and then 192 bits for 12 round, and then 256 for 14 rounds. The key size vary, and as same is the case in number of round will be varied in this case. So if the key size is 128, then the round will be 10 rounds you have to perform. So dear student, here you can see over here this for each round we have to use some expansion function, add round key expansion function that basically is we can say it key scheduling, that for each round we have to generate a new key that is based on standard first key of 128 bits. Like after passing the whole plain text by using each new key for each round, then we will get 128-bit ciphertext. Dear student, if we can see the next slide, we will have to use the basically define some basics that how our encryption algorithm evolved, what are the data unit inside the AES. So there are some basic data unit in AES like this one. Here you can see in figure 2. So data unit in AES, bytes, byte means to say you have one byte is consist of 8 bits, so B0, B1. This can be written as a row vector, or it can be written as a column vector. So whenever I say word, it means it has two uh, bits. So we can either written as a row or either written as a column. So if I can say block, block means to say this is a whole block of 16 bits. So state means to say it is state basically. This is a one state state. If you can write this whole bits into a matrix form, this will be a one state, and it means this is a basically we have four word. This is a one word, this is a second word, this is a third word, and this is a four word. Because word consists of four bits. If I can say this is a one first bit, second bit, third bit, fourth bit, then this is a W naught, and this is a W1, W2, and W3. So in that case, let me define state. What does state means? So if you can convert a block to state like this one, so you just place B naught, B1, B2, B3, so B4, B5, B6, B7. So you convert this block into a state. So inserting an expression flow is like this one, like you put this like this one, then from this one like this one, you put this four block into first column, these remaining four bit into a second column, then these four bit are placed in a third column, and the last four bits are placed in a fourth column. And that you can generate first state. So if you can get back the reverse block, so you have to place this column in a row vector as a whole. Put this in a row, and then this in another row, and this place over here. So in that case, you can just get back your from column to, you place all these column in a one standard n cross one column. So a column vector, in that case, you will get array of one dimensional array. So here basically from block to state, block is a one dimensional array, and this is a basically two dimensional array. And then if you get back, so from two dimensional to one dimensional array, you can convert. So, dear student, changing plain text to state, if you have, let us say, AESU, this is a text, and this is a hexadecimal or notation of this text to hexadecimal representation. You just put 0, 0, 12, 4 in first column, then 12, 4, 12 0 in second column, then 0 C 0 0 13 11 in a third column, and then 0 23 19 19 in a fourth column. In that case, you can change plain text into a state. So the basic structures of fundamentally AES is consists of basically four type of transformation, that is sub-byte transformation, shift row, mixed column, and add round key. Dear student, the sub-byte transformation, whenever I say this, means that we are fundamentally utilizing substitution boxes, and shift row and mixed column are basically are transformation related to permutation, and this is the last one is related with another third component of modern block server, which is around add round key. So basically, let us come up with some transformation. Dear student, as you know, the AES encryption defines a number of transformation that are to be performed on digital information. The first step of the modern Cipher, I mean to say, the advanced encryption standard is to put the digital information into a block, after which the cipher transformation are repeatedly performed over a number of encryption rounds. The number of rounds is determined by the key length, which we have discussed in last slide, which might be 10 rounds for 128 bits key, and 12 rounds for 192 bits key, and 14 rounds for 256 bit key. The, the first transformation in AES encryption cipher is substitution of information using substitution boxes. The second transformation, shift data row, means to say performing mm, shift row, and the third is mix column. The last transformation is simply exclusive or operation performed on each column using different part of encryption key. So, dear student, I have discussed these each and every component separately. So, longer the key need more round to complete. So, in order to basically combat our modern block cipher, different kind of substitution and permutations was utilized inside the actual structure of modern block ciphers. Let us start with some substitution. Like in AES, AES use substitution boxes, but these are quite different from DES substitution boxes. AES is non-fistal. It means that AES utilize at the time of encryption and at the time of decryption different substitution boxes, and these are based on strong mathematical structures. So, dear student, at the time of encryption from sender, and you can use the one substitution box, and while retrieving your plain text from Cipher at the receiving end, you have to use the invertible substitution box at the receiving end. For that, AES use two invertible transformation, means to say two invertible substitution boxes. The first transformation is sub-byte transformation, which you use the encryption side to substitute a byte who interpret the byte of two exact digit. Like the sub-byte involves 16 independent byte to byte transformation. The student, if you can see over here, let me give you the overview how substitution boxes work and how you can construct the substitution boxes that are used in advanced encryption standard. So the substitution box basically used in AES is of the transformation from Z28 to Z28, and it is basically the composition of a three further Boolean function. One is the inverse transformation, and that is inverse transformation, then linear transformation, and then translation, translation, or you can say translation. So if I can apply this S on some vector of n cross 1 or 8 cross 1, then you can write it, apply this function on X. So in the same parallel, how you can operate composition. So G of L of I of X. So where G is a translation, that translate your column vector with D unit. So in three-dimensional space. So G is a translation from G28 to Z28. If you can realize linear algebra, and you have translate some vector in 2D to 2D, so the order of the initial vector is 2 cross 1 and D will be of 2 cross 1. In that case, basically we are using a byte as our basic component in advanced encryption standard, and one byte is consists of 8 bits. So that is why, student, I just put 8-dimensional vector space. That is G of X is X XOR D. This is a translation that does translate D unit. So linear transformation I take from 8-dimensional vector space to a that simply, if you don't know vector space, leave it. So, dear student, just remember one thing. You take 8 input and that give you 8 output. Of binary. So L of x, when you take put L, apply L on x, it will generate A into x. And you can see A into x is a linear transformation. So that is why I just also keep one thing in your mind. It's a fundamental theorem of linear algebra that whenever there is a transformation, there is always a matrix of transformation, and whenever there is a matrix, there is always a linear transformation. So, dear student, you must keep this thing in your mind. L of x is when you apply L on x, then you will get into x. So it's again. Linear transformation that satisfy the linearity property of since this expression satisfy the linearity property, so it is linear transformation. So inverse transformation is again 8-dimensional vector space. So it take 8 input and map on 8 outputs. So if you can put our 8 input means to say it is a 8 class 1 column vector. Whenever you take some input as a 8 cross column vector, it will give you inverse of that column vector, which is again 8 cross 1 column vector whenever x is not 0. If x is 0, then it will give you a 0. And this is not just a 0, it is a 8 cross 8 dimensional 0, means to say it is a 8 times 0, and it can be written as a 8 cross some column vector. So dear student, once again I have to just expand this how it will work. So when G of L of I of x, when you apply x on I on x, you will get x inverse. Then apply L on x inverse. This, whenever you apply L on x, you will get A into x. If there is a inverse x inverse, then A, when apply on ax inverse, it is function that it just multiply a with any input. So when apply L in X inverse, so A into X inverse. So G is nothing. It is that when G apply on some input, so it will give you X time X XOR D. Means to say this is an input. If you apply G on this input, what G did with this input, that this is an input, then it just add D. So ultimately, you finally end up with this expression, and this is nothing. This is just the expression of your sub-byte transformation in substitution box in advanced encryption standard. So let us come up with like the student in that case, if you can see in my back slide, it is a 8 dimensions to 8 dimension. If I S is a 8 dimension to 8 dimension, to the order of matrix will be 8 cross 8, and this basically this is belong from general linear group of matrix of order 8 class 8, our binary field. So in that case it means the determinant of this matrix must be non-zero, because this is belong from general linear group of order 8, our z2. So I can say general linear group of degree 8, our binary field Z2. So in that case, dear student, if we can see this is, and x is 8 cross 1 column vector, because x is a belong from this, then it Z28 basically consists of each and every element is of 8 class 1 column vector. So if you take x, so you have to apply the inverse of x, which is, if you can take 8 class 1 column vector, so you have to take here 8 class 1 inverse of x with 8 class 1 column vector plus these are, and again 8 class 1 column vector. After applying all these computation, you will get output as a 8 class 1 column vector. So it is again in Z to 8 dimensional vector space. So you take a 8 input, and resultant will also be 8 bit binary vector. So, dear student, if I can take A as a 8 class 8 column vector, and this x inverse is just I put x naught, x1, x2, x3. This is 8 class 1 column vector. Here this x is fundamentally the inverse of x XOR with some d. So dear student, if you can look over this matrix, how I can construct this matrix. This is just based on left shift. If you know first row, that is one, the triple zero and triple one, and then one. So perform. If I take it as a first row, then perform left shift. That it means you just take this input and place it on left. So in that case, if you just apply one shift, so the one will be transmitted from right to left. In that case, the output will be 1 1 3 0 and 3 1. So if you apply another left shift to here, you can see this is a second row. This one 1 1 0. You just apply one shift, left one shift to this binary column of this matrix. So you will get this one like here. So if you apply another shift to this left shift, this means this one clockwise. Right shift. This is sorry, dear student. If you can correct over here, this is just you can perform over here the like this one from right to left. So this this is left shift. So you can perform place this one to counter clockwise in place over in this right left position. So your ultimately the one will be the which is appear in last bit will appear at the first level. So this will be triple one, triple zero, and then double one. So in same is the case, it eight row will be if you can apply shift left shift on each row, so you will get last column row of your this matrix. In that way, you can get this whole matrix. So this is one of the if you know this this first row, though ultimately the rest of the rest of the rows of these matrices can be easily be obtained by just applying left shift to this first row. So dear student, if you can look over here, if you can put zero, zero means to say 8 cross 1 column vector of zero. If there is 0 0 0 0, what you will get? This is 1 1 0 0 0 1 1 0, and this is first output, which is 63. What does it mean? Can you someone answer this? Basically, this is the hexadecimal, and if you can see over here, this is just if you put zeros, zero, zero vectors. This is means to say all are zero, 8 cross 1 column vector. All input is basically zero because when you put here zero, then inverse function is what? When x is input is zero, then it will just give you a zero. Not when there is a, element other than zero, then it will give you a inverse of this element. If x is zero, so input is zero, then it will only give you the zero. So in that case, if you can look over here, so dear student, so in that case, the whole thing is zero, and inverse of zero is zero. Actually, this is not zero, but we just apply the extra condition because in multiplicative Galois field group GF2 raised power 8 0, there is no zero. We take one condition, impose one extra condition that this zero is mapped on zero. So when you put zero, so there will be a zero. It means all these vectors are zero. In that case, we have get this one. If you can convert this, this only this vector we will get. Then it is 99. if you convert from binary to decimal, then it's basically the decimal is the student 99. So if you can convert this 99 from decimal to hexadecimal, so in that case you will get 63. So in the same way you can pass 1, inverse of 1 is 1, so you have to place 8-bit binary of 1. So if you can replace 1, so you have to place inverse of 1, which is 1, so you have to place the binary of 1 in 8 binary, in 8 binary, which is 1 0 0 0 0 0. All the other element are will be 0. In that case, dear student, you will get the second element, third element, but don't confuse with these elements. These are given in hexadecimal, and you can see this table in numerous available in number of online websites. So you just convert this from hex to decimal, then you will realize how actually this is. So why I just take hexadecimal, because I just take hexadecimal in order to shrink my calculation. Otherwise, I have to write the 8 bits of each and every element, so I am unable to put a very large data in my one slide. So same is the case with inverse. This is one of the inverse sub-byte transformation table. So which is basically the inverse of this transformation. If you can apply inverse of this transformation, then you will get this second table which is given in this slide. So let us take one example that how sub-byte transformation is applied over here. So figure 4 show how state is transformed using the sub-byte transformation. This basically also show that how your inverse sub-byte transformation perform. So dear student, if you can look over here, so 0 0, it means 0 row 0 column. Here you can see 0 row 0 column, that output will be 63. So another this one, 1 to first row second column, like this first row second column, this is E3. So here you can see uh, sorry this one is let me wait sorry, first row second column, this is C9, C9. So here you can see this C9. So this one OC, 0 row and C column. So 0 row and C column here, 81. So 0 row and C column. So if we can look over this EF and 08, it means 0 row and 8 column BF. Mm, So in that way you can perform all the calculations. So inverse transformation is just a reverse of each and every, like 63 is map on 0, and here you can see over here 12 is map on C9. So C9 is output after passing with the substitution was the inverse. Whenever there is a C9, it will replace with 12. 12. So whenever there is a 13, 13 is replaced 7D. So whenever there is a 13, if you can see over here, 1 1 first row, first row for 82, first row first column, which is 82. So, dear student, if you can see this 0C, 0 row and C column, here you can see actually I was searching in second table, so I was just little bit confused. So let me clarify. So 0 row and C column, EF, you can see over here, 0 row and C column, 0 row and C column. This is output will be EF. So I put EF. So 0 row, 8 column. So here you can see 0 row, 8 column. This is 30. So dear student, here you can see 30. So the inverse, how I can apply inverse transformation. For inverse transformation, that I have to inverse table which is given in table 2. So 6 3 I have to apply inverse transformation. 6 3 means a sixth row and third column in this table, second table. Sixth row, sixth row and third column. This is 0 0. Here you can see this is 0 0. Okay. So C9, 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 C row and 9 column. Here you can see this is 12. So here you can see this is 12. So inverse transformation, if you can see, input is for inverse transformation, output will be input and input will be output. So if you can find out the inverse of any substitution boxes, if there is an input and its corresponding output, just shift it output with input and input with output, then you will get the inverse substitution box in that case. So dear student, this is same thing which I have did in my last table, and but it is written in a quite sub-byte and sub-nibble and inverse transformation. So this is one of the basically the sub-byte transformation or the inverse sub-byte transformation means it's a substitution boxes and it's inverse substitution box. So it is if you have an initial state, then you take it inverse of that state and then byte to matrix transformation. This will be in some decimal or bytes. There will be a bits, some bits. So you convert this bit into a column vector and multiply this with a matrix 8 cross 1 matrix, and you ultimately this calculation from this calculation the output will be C0 C1 up to C7. Then you take this and XOR with this column vector which we have discussed in this column vector, this one. So, dear student, ultimately, if we add up and then matrix to bytes, and ultimately after XORing this output with our column vector D, so ultimately we will get D0, D1, D2, D7, which is again 8 bits. So we have to convert this 8 bits again into matrix of 8 cross 1 column, which is again in 8 cross 1 column. So inverse is you can take this as inverse and apply the first you have to this is a basically input basically Cipher, and you can take to C0 C1 you have to uh, eliminate this column vector from here, then apply the inverse of this matrix with this output from this step. This is C0, then you will get B0, B1. Then convert this and then calculate the inverse of this column vector in Galva feed GF2 raised to power 8. In that case, you will get one state from sub-byte. So this kind of transformation is required at the time of decryption, and this kind of transformation is required at the time of encryption. So let us take one example. Let us show that byte 03, it is again given in hexadecimal notation. So its binary representation is given over here. This is 00001100. It's transformed to EF double one double one and double one one zero by sub byte routine, a sub byte transformation block to 0C by inverse subroutine. So you have to use sub-byte means to say substitution boxes, and inverse sub-byte means inverse substitution box. So the inverse of 0C is basically B0 in basically Galva feed 2 raised power 8. If I can say this, how one can write this? This is alpha 3 plus alpha 2, and this is alpha 7 plus alpha 6 plus alpha. I had sorry. Let us take B0. So what is the binary of B0? So the binary of B0 will be 1011 and 0000. So 10110000 four times zero. So ultimately, what you have to do, you have just apply. If I say in Galva free GF2 raised power 4, I would like to calculate the inverse of alpha. So on GF2 raised power 4, alpha on alpha 15, I'll get 1. So alpha, in order to calculate the inverse of alpha, what I will have to do, so I have to apply alpha with alpha 14, then I will get alpha 15, then which is again equivalent to 1. So inverse of alpha is alpha 14, and the inverse of alpha square is alpha 13, then inverse of alpha 3 is alpha 12. So in that same is the case, if you convert this OC in binary, there will be some alphas, and you have to calculate the alpha of this term with some other alpha which make it alpha 255, and at alpha 255 the Galvavi GF2 raised power 4, the alpha at alpha 255 is equivalent to 1. So in that case, you have to calculate the inverse in Galvavi GF2 raised power GF2 raised power 8. So inverse of OC in Galva field GF2 is BO. It is again written in a hexa, which means that B is 10110000. B means to say I mean that B not B1. So I take just one element and then take its inverse. I mean so that it is a B, the B in the form of binary vector. So the I take this just as in a diagram. This is some element. I take it inverse and then convert this inverse into a matrix form of 8 class 1 column vector. So if you can look over here, this is the one element. You can write it in term of binary and calculate inverse in Galva feed GF2 as well, and calculate transform this hexa to binary, which is equal again 8 cross 1 column vector. So you have to multiply matrix A, which is of 8 cross 8 column matrix. This one X. Don't be confused. You can, if you are confused, then you can write in place of X, you can write A, since I have used in my previous slide when A here. So you can also use instead of X, you can use the A as a matrix. So here basically X is as a matrix, so you have to apply the inverse of B with X, which is a cross-home column vector. So you can get again C as again a cross-home column vector, and so I can say this one just multiply this and this inverse of this element. I call it as a C, and then I add C with this column vector. which is D in my previous slides number, let's say this one, this. So here you can see student. So finally, I get if I add XOR basically D C with basically my this operation like this one I XOR add, and if element is 2, then I make divide it by 2 and calculate its remainder. So dear student, if you can see over here, I finally I get D, which is again of 8 cross 1 column vector, and this is this one. D means to say column vector of mat binary 8 class 1. So you have to apply the inverse binary operation by yourself, and this calculation we have already done in this case over here. In this case we have already done this calculation, but here I have to just show you in a block diagram how it actually works. So permutations is again the how you can shift something. So shift from mixed column add round key. If you have some state like 4 cross 4 column matrix. So left shift, I mean to say from this to this. So you have to apply some left shift. So you can just put from first place to last one. So in this case, you can see over here this one second, first, second, third, and fourth position. So you will have to apply. There will be no change in first row, there will be a one change in second row. That is, you have to just translate these from left right to left. So this position will be on last one, and the second position will be placed on first one. So in that case, you can say each and every uh, element of the first row will be a chain, uh, and we call it one shift. And here we have to apply two shift. I mean to say, if you can replace this from left to right, so this white block will be placed at last, and the dark which is gray box will be on first position. In that case, each and every box will be dispersed one unit towards uh, right to left. So in that case, we have to apply two shift on third, and three shift to basically fourth row. So in that case, we can say this is our next state is the final state after performing permutation. So if I can give you the example, if you have an input in like this one, hexadecimal notation, so I can put this all these calculate this hexadecimal in a state that's 6C, FC, then C9, then FA. I put each and two element in state of 4 cross 4 column vector. Here you can see zero shift means to say the row will remain same. One shift, it means that you have to apply a one shift. So for that to this row, it means this will be placed from left to right. So this position will be placed from first to fourth, and this will be a first to second to first, and this position will be third position in the second row. This will be placed from third to second position. In that way, you have to perform another shift to this one. It means two shift. If you apply another shift to this row, it means there is a three shift. So ultimately, the output will be here. You can if you can see over here, the output is 63 F2, then F2, then 70, then D4, E4, then C9. Then you can read like column wise reading. So ultimately the last output will be 82. So in that case you have apply shift row, and for mixed column, dear student, you have to apply a 4 plus 4 matrix. We call it constant matrix, and all component of this last step, which last state, which in which we have applied shift row. And so each and every column of shift row is taken and apply repeatedly in that place with 4 cross 4 column, 4 cross 4 matrix. In that way we are doing nothing, it is just a mixed column operation. So if you can look over here, this is our one of the mixed column of 4 cross 4, and the inverse of this mixed column is 4 plus 4. So here you can see this is our state, which is 4 plus 1 column vector. So you have to take one, any one of column vector, which is 4 plus 1. Then this column is 4 plus 1. This is again 4 plus 1, and this is again 4 plus 1. So you have to take any column vector like this one and multiply this with 4 plus 4 constant matrix, and you will get this new states. For each and every column, you have to apply this column transformation or mixing column transformation. So the mixed column and inverse mixed column transformation are inverse of each other. Like if you can place this one is the first column, this one. If you multiply this 4 cross 1 column with this 4 cross 4 matrix, then ultimately you will get 4 cross 1, first 4 cross 1 column vector. So in that case, if you can take this one as a 4 cross 1 column vector, then multiply it with the constant matrix which is given over here in this one. This is a 4 class 1 column, this is a 4 class 1 matrix. You have to apply this with second column of this state, then the same with third column of this state, and same with fourth column of this state, and each and every column of this state will be multiplied with 4 class 4 matrix, and ultimately you will get 4 plus 1 column vector for each and every corresponding to each and every column of this state, and ultimately you will get another state which is called mixed column. So dear student, this is all about some of the component of advanced encryption standard. I hope you enjoy my lecture today, but keep one thing in your mind. I have just quit my lecture over here, so you have to first realize and understand these basics of advanced encryption algorithm. In next time, I will have to add one more component of advanced encryption standard, and then we will have to apply this whole small components and then combine them in order to develop a modern block cipher, and in order to understand what actually advanced encryption standard means. So, dear student, this advanced encryption algorithm is one of the most important tool in modern cryptography, and every small or lightweight or any machine, any modern encryption, any modern embedded software basically utilize this encryption algorithm to secure its digital information. If you can see over here, DOT, drones of things, even drones are also using this advanced encryption algorithm in order to secure its information, or while they're sending their information to some remote destination, so they have to be use some encryption algorithm in order to add protection layer to its digital information. And moreover, dear student, I just slow down my pace because this is the core heart of today. While you whenever you discussing anything, the AES is will always be there. In order to understand this, you have to understand these components which we have discussed today in our class. Uh, Till then, Allah Hafiz. Thank you all, and please stay at home and stay safe. Allah Hafiz.